Welcome back to this course on blockchain and its applications. So, till now I guess that you already have a fairly good understanding about blockchain as a data structure. So, you have seen that how we use hash chain to connect the individual blocks, and then it forms the end-to-end chain which is secured from external attacks, and it provides the required properties that we want to have or want to see in a blockchain. Now, once we have that chain, and by virtue this is a decentralized data structure, that basically means every participants in the blockchain network, they keep a local copy of the blockchain. Now, once every participants in the network keep a local copy of the blockchain, one of the primary requirements that we have seen earlier is to ensure that everyone has the same copy of the blockchain. So, this particular protocol, as we discussed earlier, it is called a consensus mechanism, which is a kind of very prominent and very important feature any distributed system must have. So, in today's lecture as well as in subsequent lectures, we are going to look into the consensus mechanism in a blockchain, and we are going to see that how a blockchain architecture uses this consensus mechanism to achieve the required properties. Now, to start with, I would like to remind you about our initial discussion where we talked about that although there are vast literature in distributed consensus that people have worked upon from 1980s and 1990s during that time, but unfortunately those consensus algorithms which are there, they are mostly applicable for a closed network, means where every participant knows each other and they can work on a message passing interface. But in case of our typical open blockchain application that we use in cryptocurrency or similar kind of open environment, what we have seen that the participants do not know each other. So, anyone can join in the blockchain network, and at the same time anyone can leave from the network. Now, in this particular scenario, our challenge is to ensure that we should come up with a consensus mechanism, and again this is a kind of distributed system, this is a kind of asynchronous distributed system. So, whenever we are thinking of designing a consensus mechanism for a asynchronous distributed system, we need to keep in mind the FLP impossibility that we mentioned earlier. So, which basically says that it is impossible to reach consensus in an asynchronous system even with a single crash fault. So, what we have seen earlier that the classical distributed consensus mechanism, they have given more priority to safety over liveness, and that way we have a vast literature of different types of consensus algorithms, but those consensus algorithms are broadly inapplicable in the context of open blockchain network. So, today we are going to look into that in a permissionless model of blockchain or in an open model of blockchain, how can we effectively design a consensus mechanism, or just to remind you that we briefly mentioned about earlier the proof of work based consensus. So, today we are going to look into the details of this proof of work based consensus, and we will see that how this proof of work based consensus helps you to achieve agreement in a open permissionless network in an asynchronous environment. So, to proceed further, today we are going to have a kind of broad overview of the permissionless model and how it works. Then we will see the consensus requirements for open networks, and we will consider or we will discuss about the different kind of faults that may occur in an open network. And finally, we will look into the FLP impossibility. So, basically we will reiterate the FLP impossibility in the context of a distributed system, and then we will see that how this FLP impossibility is applicable in the context of an open consensus mechanism. So, today the broad topics that we are going to cover are the permissionless models, the notion of synchronous and asynchronous channels in a distributed system, the different kind of failures that can happen in a distributed system, and finally this safety versus liveness dilemma which we have in the context of FLP impossibility in the context of a distributed system. So, to start with, let us have a brief idea, or rather recap our vision, our idea about this permissionless model. So, this permissionless model broadly works on an open network. So, what is mean by an open network? So, an open network is basically a network where anyone can join and initiate transactions. So, the ideal example of an open network is the cryptocurrency network. So, in the context of cryptocurrency network, we have seen earlier that anyone should be able to join the Bitcoin network and they should be able to initiate a transaction in the Bitcoin network. So, for that you should not have or you should not need any kind of pre-authentication or pre-authorization. Rather, you will use this idea of digital signature through which the others will validate you, others will find out that this transaction has originated from someone who possesses a digital signature, and after that we can or we should be able to verify the transactions with the help of the digital signature and the cryptographic technique. And once this verification is done, then the network should be able to incorporate the transactions in the blockchain in case the transaction is a valid transaction. Now, that way in a open network or in a kind of complete permissionless setting, what we call it, anyone should be able to join and initiate an transaction. So, they do not need any kind of registration or pre-authorization or something like that. So, unlike the typical transaction environment that we have seen nowadays in banking environment, where you need to provide something called the KYC, the know your customer form, where you need to prove your identity and you need to say that you are a valid person, and then the transaction is initiated against your name or rather against your account number, which is an unique number given to you. So, that way the bank will be able to track that what transactions you are making, and in the same way the government will be able to find out that who are making what transactions and all these details. In a cryptocurrency network or a Bitcoin network, we do not want to have this kind of monitoring or this kind of governance. So, we want to have a kind of monetary system where no one would be able to track your transactions, no one would be able to find out that Sandeep Chakraborty has this much amount of money and this much amount of money he has transacted today from his account to this particular account. So, because we want such kind of open environment, and as I have mentioned earlier that we do not want to go to the debate about whether cryptocurrency should be legal or illegal, or whether the government should ban these cryptocurrencies, but rather we would we will put more focus on the technology behind cryptocurrencies. So, that is the kind of setup that we have, which we call as a kind of permissionless model. Now, in permissionless model, just like a participant can join the network and initiate the transaction, participants are also free to leave the network and join later on. So, that means at any instance of time you cannot say that this many number of participants are participating in the transaction procedure. The network is a kind of complete dynamic network, and rather I would say it is a kind of complete untractable network. Now, in such kind of network setting, we are going to design a kind of consensus mechanism, and that is our objective that we want to satisfy. So, the assumption behind this entire consensus procedure that we are going to discuss today is that more than 50% of the participants are honest in the network. So, you remember, so I have heard a lot of debate around blockchain, and people keep on saying that blockchain is a technology that can revolutionize, that can prevent any kind of fraud. So, if you remember, on my first class I mentioned that it is not true. Blockchain also has its limitation. There cannot be any kind of free lunch. So, whenever you are designing any technology, that technology has certain amount or certain kind of limitations, and that is the kind of limitation that blockchain has. So, blockchain makes an assumption that more than 50% of your participants are honest. Now, whenever you are making such kind of assumption, you really need a very large network, because if your network has only 10 participants, now for an attacker it is much easier to compromise 5 or 6 participants out of the 10 participants. Well, but if your network has millions of users, then it would be very difficult for an attacker to compromise that many number of users. Well, so this is the basic principle or basic idea here, And whenever we design a technology on an open blockchain network, we believe that it will work in a societal scale, and in any society you cannot have more than 50% of the participants as dishonest. So, if majority of the participants in a society are dishonest, then the society cannot run well. So, this is the kind of primitive idea or the prime idea that open blockchain network considers, or rather an open blockchain network assumes well, and the entire design of the consensus mechanism and the security of the blockchain network is based on this particular assumption, that you can have at most 50 or 49% of the participants as the dishonest participants of the attacker. So, the attacker cannot gain control over more than 50% of the participants, and as you can understand, this is only possible when you can ensure that your network is really very large. Well, so in a small network or in a community network, this is very difficult to ensure. You will not be able to ensure that, because on a small network it would be much more easier for an attacker to gain control over more than 50% of the participants. But if your network is really very large, if your network has millions of users, then it will be very difficult for the attacker to gain control of more than 50% of its participants. Now, there are multiple permissionless models which are available. We mentioned that earlier, and the most prominent models are the Bitcoin network and the Ethereum network. I would like to mention both the network here, because Bitcoin network is a cryptocurrency network, and rather there are many other cryptocurrency networks which work on this principle of a open blockchain network or a permissionless blockchain network. But at the same time, you should keep in mind that the financial application or the cryptocurrency applications are not the only applications on top of Bitcoin network. You have Ethereum in hand, that Ethereum provides. So, earlier we have seen in very brief that Ethereum provides the support for decentralized application design, or what they call it as dApps or dApps. Now, using dApps you can design very interesting games. I remember that I had given you the example of one of such games named CryptoKitties, which I personally like, and I guess that all of you have already played that game by this time. So, this is a kind of gaming model where you do not need any game server, or you do not need to host any explicit gaming server. It entirely depends on the participants who are currently playing that game or who are currently participated in that game, right. And in that way, it is a kind of entire decentralized architecture, decentralized gaming architecture. But again, while you are designing such kind of gaming architecture, you need to keep in mind that your gaming platform need to be really large, in the sense that there should be many participants who are participating in your gaming network. If it happens to be that there are only handful number of participants, say 5 participants, and you cannot ensure that there are more than 2 participants at a single instance who are participating in the game, then you cannot run that system. So, the gaming architecture that you are planning to design on Ethereum dApp platforms, that should also attract a large number of users to participate or to play that game. Well, so apart from gaming, if you just browse with Ethereum dApps, you will see that there are many interesting dApps which have been developed by the open source community. People have developed different kind of applications by using the Ethereum smart contract, which uses a permissionless blockchain model, and that way you have really a large spectra of applications which you can support on top of the permissionless model. Now, if we try to look into the challenges of consensus, achieving consensus in a permissionless model, we have mentioned that earlier. This is just a kind of recap so that you can remind the core idea. So, the first thing is that the participants, they do not know each other. Well, so when the participants do not know each other, they cannot use message passing, and that we have seen earlier, and that is primarily the reason because of which we cannot use the classical distributed consensus algorithm in the context of open blockchain network or permissionless blockchain network. Now, the second challenge that I have, or that we have, is that anyone can propose a new block. Well, so again it is a kind of entire open network, and when it is an entirely open network, any participant can propose a new block. Well, and later on we are going to see the Bitcoin mining procedure, or the mining procedure that is generally followed in any kind of proof of work blockchain. So, there are a set of participants who try to mine a new block or who try to generate a new block. Well, and out of those many blocks, any block can be added in the blockchain. So, the question comes that how will you find out the participants or how will you find out someone who should add the next block in the blockchain? Now, this is again a very crucial question. Why this is a crucial question? Because you need to ensure that in different rounds of the protocol, different participants should be able to add the next block. Why that is so? Because if it happens to be that I am the only person who is going to add multiple blocks in the blockchain and who is going to say add the next 100 blocks in the blockchain, then at least a portion of the network becomes under my control. So, that way if I start doing some kind of misbehavior or if I am a kind of attacker or a dishonest participant, I can possibly deceive the network from its goal. Well, so that way we need a true decentralization in the architecture. So, we need to ensure if there are 100 different participants and if we are considering 100 different rounds, then in every round means out of those 100 participants, one participant should be selected in such a way so that all 100 participants get a chance. So, that way you can design a kind of complete distributed architecture, and that way if the attacker can collude one of the participants or two of the participants or even 49 of the participants, so there are 51 other participants which are honest and they can make the system run. Well, so this is the kind of idea that we have and we work with this particular idea. So, we need a real decentralized architecture. The third assumption that we have is that, or the third challenge rather that we have is that our typical communication network is asynchronous, right. So, that basically means whenever you are going to send a message over an internet, your message might get lost, your message might received out of order. Well, so someone of you may ask me the question that, sir, there is this TCP or transmission control protocol and over the internet that can support reliability. Well, then why we are assuming that asynchronous behavior? But here you remember that this TCP is a kind of end-to-end protocol, and here we are actually talking about an application layer peer-to-peer network. Now, whenever we are talking about an application layer peer-to-peer network and I am sending certain data to my lower layer of the network protocol stack, it might also happen that certain of the applications they behave fraudulently and they drop my packets. Well, so one typical example can be something like this. Say let me try to put up a scenario. So, you have say multiple different nodes and these nodes are connected with each other. Now, when these nodes are connected with each other, there is no guarantee that every node is connected with other nodes. Now, assume that one of these nodes, say this particular node, it generates a message n. Now, this message need to broadcast across the network. Now, whenever I am trying to broadcast this message across the network, you see that you cannot reach all the participants with a single broadcast. So, that means it is not like that you can create a direct connectivity and you can send the message. Well, so what we do here, we use a protocol which is called the gossip protocol. So, gossip is an application layer protocol. What is mean by gossip? Gossip basically means that this person, it is connected to two other persons. So, it will send the message to those two persons with whom they are connected with or with whom it is connected with. Then this person, this guy will propagate the message further, well, to the participants with whom it is connected. Similarly, this guy will send the messages further. So, that way in multi-hop fashion the message will get propagated on top of this peer-to-peer network. Now, here say as I was mentioning that it is a more like a application layer message passing. So, that way whenever two persons are sending the message directly, under that I might have used the TCP protocol. Well, and again this link does not mean that they are directly connected over a wired network. So, it might happen that it is a logical link over the network. Well, so for example, I am I am having a peer and that peer is there in say Australia, and if that peer is sitting at Australia, obviously I cannot have a direct physical communication link which is connected to my computer with that person's computer at Australia. The message is going over the network. Now I can set up a TCP connection with that person and send the message to that person. Now what if this particular person who is taking the message from me, this particular message person is a faulty person or a faulty node. That means it has certain software bug because of which the message is getting dropped. Okay. So TCP cannot prevent such kind of message drop. Why? Because TCP is just ensuring that at the network layer, at the underlying network is reliably transmitting the message from say this guy, say I am naming this guy as x1 to this guy I am naming it as x2. Well, but it is more of a application side. So the application on x2 it was currently have certain kind of fraudulent behavior, or maybe the application is not running, or maybe there is a software crash or operating system crash because of which it is not been able to get the message and broadcast it further. Well, so that way the message might get lost. Well, and because of the same reason it might also happen that at the application layer you start receiving the messages out of order. Well, so that is one of the case, and the second important case is that we are working on a complete distributed network. Now, whenever we are working on a complete distributed network, we do not have any kind of global clock. You will never be able to ensure that the computer clock of multiple different participants are exactly synchronized. Well, so there would always be a clock drift. So that means if my clock says the current time is 3 hours 55 minutes 20 seconds, another machine may say that the current time is 3 hours 55 minutes 21 second. Well, so there may be such kind of clock drift even if the clock drift is in the order of millisecond. So that way over a distributed network it is very difficult to ensure the clock synchronization. So there are protocols like NTP, network time protocol, or such kind of things, but NTP again cannot guarantee perfect synchronization across the clock. There is always some amount of clock drift. So because of such kind of reasons that you do not have perfect clock synchronization, the messages may be received out of order. It might happen that a participants or a node in the slow network might have not seen the entire message and read the message later on. We consider that the network on which we are going to work on, it is a kind of asynchronous network. And the moment I consider that my network is an asynchronous network and it is a distributed network, I have this FLP impossibility in mind. So the FLP impossibility basically tells me that well, you cannot achieve a perfect consensus by supporting safety and liveness together. So either I have to give priority to safety or I have to give priority to liveness, but I cannot give priority to both safety and liveness together. Well, so these are the kind of challenges that we have, and another interesting stuff that we have, as I was mentioning, that different participants can see the block in different order. Well, and how this ordering actually important. So for example, I have a blockchain, and in the global blockchain I have block 1 followed by block 2 and followed by block 3. Now different people are proposing the block. Now it might happen that this guy it receives block 3 first, and after it has received block 3, then it receives say, so after it has received block 3, then it has received block 2. Okay. So here the interesting fact is that although in my global blockchain the block 2 precedes block 3, but because say I am in a slow network, it might happen that this particular network on which it is connected to this girl, this is a slow network, and this is a fast network. Now, because of that reason, the node it has received B3 first followed by B2. Now, because that can always happen in a network, I need to have a mechanism to understand that well this is the block which has been generated first and this is the block that have been generated. So, such kind of out of order message I should incorporate while designing the underlying communication protocol or rather the underlying distributed system architecture. So, these are the kind of requirements or challenges that we have while we are talking about the consensus mechanism on the blockchain, and the final important challenge that I have that I mentioned earlier as well, that any type of monopoly needs to be prevented. Well, so that way a single user or a group of users should not be able to gain the control over the network. Well, and remember that we are working on an environment where we do not trust anyone. Well, so that way what might happen, that an attacker might collude the other participants, and when an attacker is colluding other participants, I need to ensure that attacker and the colluding nodes together, they should not gain the majority control over the network. Well, or a single person should not be able to generate multiple blocks, multiple consecutive blocks. Well, so any such kind of monopoly I need to prevent to make sure that the system is working perfectly. Now, I have mentioned that earlier, here just a kind of more formal way of defining a synchronous and an asynchronous network. So, a synchronous network, I am sure that I will get the message in real time. That means, I would have theoretically I will have no delay in receiving the message, or I will have some very minimum delay on receiving the message. That means, once a message is originated, immediately or within a minor delay I should be able to see the message. There is no message loss or there is no out of order message. Whereas, in an asynchronous network, I am not sure whether and when the message will arrive. Well, so it might happen that a message has lost and the message is not arriving to me. It might happen that a message will arrive me after 2 hours or after 3 hours. Well, and obviously for a real time environment, I cannot wait for 2 hours or 3 hours to receive the message. Well, so that way designing the protocol or designing the system over a asynchronous network is much more challenging. So, if I then try to consider the different kind of faults that can happen in a network. So, the first type of fault we call it as the crash fault. So, the crash fault basically means a node stops responding. So, here in this example, this node stops responding and does not send any further message. So, this is a kind of crash fault that the entire node has crashed, that might be either due to some hardware bug or some software bug. The second type of fault that we have is the link fault or the network fault. That means, one link has stopped responding and that link fails to deliver the message. So, in this case, although this guy is able to send the message to other two nodes, that links are active, but the third link is down, because of which it is not been able to send the message. So, this crash fault and link fault are still much more easier to handle, as we will see later on. So, the major challenge comes in the context of a fault which we call as the Byzantine fault. So, why we call it as a Byzantine fault, that we discuss later on. So, the broad idea behind the Byzantine fault is that the node starts behaving maliciously. So, this kind of Byzantine fault typically comes from a kind of attack over the network. So, here is an example of the Byzantine fault. Say, assume that this node is going to propagate the block information to one of its participant. It says that the next block is B2, to other peer it says that the next block is B4. Well, so this is the kind of behavior that we tell as the Byzantine behavior or a kind of malicious behavior. Well, later on we will see that from where this name Byzantine came from. Then in an asynchronous network, we need to keep in mind this FLP impossibility. So, the FLP impossibility says that consensus is not possible in a perfect asynchronous network, even with a single crash fault. So, that basically means that we cannot ensure safety and liveness simultaneously. And what we have seen earlier, we have mentioned this earlier, that this Nakamoto consensus or the proof of work that have been designed in the context of Bitcoin blockchain, it gives more priority to liveness compared to safety. So, the immediate focus of this Nakamoto consensus is that, well, within a fixed amount of time you try to add the next block. So, whether that it is safe to add that block, that we can satisfy later on, and what is meant by safety here, precisely here, that we are going to discuss in details in the next lecture. So, let us quickly look into the consensus problem. So, my consensus problem is something like this. I have an existing blockchain, I have multiple nodes who are going to add blocks in the blockchain. Now, whenever I have multiple nodes who are going to add block in the blockchain, these nodes we term as the miner. Why we call them as the miner, we will see in the next lecture. Now, every miner, they maintain something called the unconfirmed transaction list. So, here if you go to this link, you can actually see the unconfirmed transaction list in the context of Bitcoin, and then as the different transactions are propagated in the network, this unconfirmed transaction list is getting populated with the information. Now, one important thing to remember here is that because we are talking about an asynchronous network, it is not necessary that every miner will see every transaction. So, that way it might happen that miner 2 has not seen transaction 16, well, whereas transaction 17 has been seen by all the miners. So, that way say the next transaction 22, it has not been seen by miner 1. So, that way the transaction gets propagated and every miner populates unconfirmed transaction list, and my question that I have, that who is the miner or who is going to add the next block in the blockchain. So, this is the question which we are going to solve in this open consensus problem. Well, so in conclusion, so what we have seen today is that message passing is not possible over an open network, and we have reiterated the FLP impossibility in this context, and what we see that we give more priority to liveness. In the next lecture, we are going to look into much more details, and this particular feature is more suitable for blockchain. So, the idea is that you include the correct block, whether that block is final or not, that we will think later on. Well, and finally, we have seen that different miners see different blocks. So, which one to add? Well, so that is the kind of questions we are going to answer next. So, that is all about today's class. Thanks all for attending. So, we are going to take it further in the next class.